Everybody, my name is Eric, and I'm one of the organizers of the AppliedAI.ml meetup. The other organizers are Jan, Daniel, and Justin. Justin wasn't able to join us tonight. He had a previous commitment with family. All right, so before Nick's presentation this evening, I'll go through a few housekeeping items. That won't take too long. I know we have an interesting topic here, so I don't want to take too much time there. So first, I want to take the time to welcome all of you to our meetup this evening, especially if you're new to our meetup. Please accept a warm welcome from us. If you've joined us in the past, thank you and welcome as well. All right, I'm taking a look at my notes here to make sure I'm not missing anything. All right, for those people that are new, I want to mention that our meetup is on the first Thursday of every month. And so for our next meetup, it's going to be on September 3rd. We have an equally interesting topic and impressive presenter. The topic of that meetup is going to be AI in precision agriculture. So interesting stuff. This is not like your grandma or grandfather's agriculture anymore. It's high-tech stuff. All right. One other item I want to bring up today is we have every fall in October, we've had an IoT Hack Day. We've had 6 to date. So this is a tradition we've been carrying on since 2014. If you're not familiar with our IoT Hack Day, it's we get 10 to 15 rooms in a giant, 10 to 15 teams in a giant room. And these teams spend 12 hours from 8 a.m. until 8 p.m. to build a connected device to solve a problem they're passionate about. Also, just to build cool stuff. It doesn't have to be a problem you're itching to solve. It could be doing stuff for fun. All right, so the day runs from 8 a.m. until 8 p.m. We usually cater lunch and dinner and provide lots of caffeine. We never run out of caffeine. And so obviously because of COVID, COVID threw wrench into the gearworks. We're not gonna be doing the same IoT Hack Day we've always done. We're in the thick of planning, and as soon as we have some details firmed up, we'll be sharing those. So I think I wanna say, give us a month and we'll share more details about what we're gonna be doing in October. All right, so the housekeeping stuff is out of the way. So I'm gonna go ahead and introduce our presenter today. Our presenter is Nick Haller. Nick is a PhD candidate at the University of Minnesota's Department of Computer Science and Engineering, right here in the Twin Cities. And his research focus is the development and validation of clinical prediction models to classify risk and plan for treatments for cancers that affect the urinary and reproductive systems. So Nick is, I was reading up about Nick, and he's a very impressive individual. So in 2019, he was the lead organizer for the KITS Challenge. KITS as in K-I-T-S. KITS stands for Kidney Tumor Segmentation. So this is a challenge that takes place every 2 years. So worldwide, there are about 400,000 new cases of kidney cancer. And the way kidney cancer is treated is primarily through surgery. And among other factors, when you're treating kidney cancer, the most important part, one of the most important things in planning for a successful surgical outcome is to understand the tumor morphology. By that I mean you have to know the size, the location, and the depth of that tumor. So KITS' goal is to accelerate the development of reliable tumor segmentation methodologies. Nick was also the lead organizer for the 2019 Labels workshop. So Label stands for Large Scale Annotation of Biomedical Data and Expert Label Synthesis. And the primary focus of that yearly workshop is to create imaging data sets for machine learning. So, you guys are in for a treat, in for a really good presentation. And without much further ado, before I let Nick take over, is one thing I want to mention is please take a look at your microphone, mute it so that we can keep the background noise to a minimum. Nick is very generous enough with his time. He's going to be taking questions after the presentation. So please, as Nick presents, ready your questions so that when he's done, you can ask. So without much further ado, I wanna present Nick. Nick, please take it away.
Sure. Well, thank you so much for that introduction. That's really nice of you. Yeah, that was, I mean, a great way to start off, because I'm going to be talking a little bit about labels and a little bit about kits today too. So it's good that you've seen it already. I think what I'll do is just share my screen and pull my slides up there. It looks like it says host disabled. I have this problem a lot too.
There we go.
There it goes.
I made your cost.
Sweet. So everyone can see that, I hope. And
yes.
Present here. All right. Great. So as Eric said, I'm a third year, soon to be fourth year PhD student here at the University of Minnesota. Really awesome to see a meetup group here in the Twin Cities. You know, it's more fun to do this stuff with people. So I think it's really cool that groups like this get together. And, you know, I was surprised I hadn't heard about you guys, but I'll definitely be signing on in the future. And thanks for the invitation. You know, it's an honor to come and speak, and I'm always happy to share my work. So the agenda today, I'll be starting with a background. You know, I'm not sure what everyone's coming in with, so I just want to sort of give us all on the same page and make sure we're using the same terms about deep neural networks and stuff like that. It would be pretty, try not to get too technical with it, but just, you know, just general background. And then I'll have 5 questions that I'm going to go over. And I think these are, to me, the most interesting questions in medical image analysis research right now. And I'll give you sort of my perspective on it. You know, I have to disclose that I'm biased. You know, I'm a segmentation person, and, you know, I've formed opinions over, you know, 3 or so years in the field. I'm not going to try to hide those biases and pretend I don't have opinions on the answers to these questions, but they are open, you know, so I'd love it if people thought about them themselves and sort of gave me pushback on some of the answers that I'm going to give. But yeah, I guess I'll just jump into it then. Cool. So starting with the background, the workflow for supervised machine learning. And by the way, supervised learning is going to be sort of the whole scope of the talk. I'm not going to talk much about GANs or anything like that. People are doing some crazy stuff with that in medical imaging, but it's not really my area, so I don't feel great talking about it. I'll just be talking mostly about the supervised setting and using sort of classification as, I guess, sort of an analogy for all of supervised learning. It is what I work on most with segmentation. And I think, you know, the things that I'll say about it are pretty general, so it won't limit us too much, I hope. So when you're doing supervised learning, right, and this will be familiar to most, you collect a bunch of pairs of inputs and outputs. That's your data set. And then right away you choose a test set, right? You section out some of your data set based on some criteria. Could be totally random, could be the timestamp of the data, it could be where the data was collected. And you decide that that's the data that I'm going to use to get an objective measure of how well my methods do on data that they haven't seen before, right? So you only touch that once, and that's really important, especially in medical imaging. You don't touch that data set multiple times and sort of tune your your training procedure based on what does well in the test set. You really have to use it only once so that it is an objective measure. So then what you do is you define a performance metric. So that's sort of the way that you decide how well your model performs on that test set. And then an objective function, right, which is very similar to the performance. It's hopefully fairly well correlated with the performance metric or anti-correlated. And the only difference is that objective is differentiable, right? Because basically all of deep learning these days is based on gradient-based optimization. So you need those gradients, you need to be able to take the derivative of that objective. You define a class of hypotheses, mostly known as an architecture, right? You can think of each parameter setting for an architecture as a different hypothesis within your class. So that's kind of a learning theory term, but architecture is probably more commonly used. And then you search for the hypothesis that optimizes that objective function. So that's that optimization procedure, things like ADAM or stochastic gradient descent or what are the other ones that I'm not thinking of? You guys know them. And then you try to estimate your holdout performance. And this is before you're touching the test set, right? So this is things like cross-validation. You section off sort of a second test set where you measure your performance on that one. You decide, I like it or I don't like it. If you like it, then you move on to the test set, get that objective measure, and then move on to reporting it or deploying it. But if you don't like it, you can always start over, right? And that doesn't give you too bad of a problem with overfitting as long as you don't touch that test set at that stage. So you can repeat 3 through 7 as many times as you want. Usually it's quite a few times because there's a lot of decisions to make and they do affect the performance quite a lot. And so you do that until you're satisfied and then you move on. All right, so common performance metrics. Again, I'm a segmentation person, so these are the ones I see a lot. Accuracy, precision, recall, F-beta score. Accuracy is probably the most familiar to everyone in the crowd. That's the proportion of the voxels or the proportion of cases that were correctly classified. Precision is of those that are classified as positive, what proportion really were positive, right? So if you just go around classifying everything as positive, your precision is going to be low. But your recall will be high, and that's the one below it. So that's a proportion of those that were truly positive, what proportion were classified as positive. So if you never label anything as positive, then your recall is going to be low, but potentially your precision's high as long as you get 1 there in the correct region. And then an F-beta score is just a way to combine the precision and recall. And beta is just sort of the decision you make about what's more important, precision or recall. And if you think they're equally important, you use a beta equals 1, that's called the dice score. If you think precision is more important, you could use a beta lower than 1, like 0.5 or 0.25. If you think recall is more important, then you can use a 2 or a 4. Recall is typically the more important one in medical imaging, at least in cancer, because we typically weight false negatives as very serious, right? If you miss a tumor that's actually there, then that could be, detrimental. Whereas if you predict a false positive, if you predict something as tumor when it's actually healthy, a lot of times it's not the end of the world. Some people are questioning that these days because they're saying, well, we're doing quite a lot of overtreatment, especially of renal masses, which is something that I work on a lot. So I usually use a beta of 1. But anyway, these are just common things that you'll see in the KITS challenge, which has already been mentioned. We used a beta of 1, the dice score. So the components of a deep neural network or deep learning, you've got your input structure and your output structure. And to me, these are the two sort of defining characteristics. I don't spend a lot of time worrying about architectures because I'm more of a deployment and validation person. But the architecture is just sort of the bridge between the input and the output. Really the only requirement on the architecture is that it takes something that's the correct size, which is the input structure, and produces something which is the correct size, which is the output structure. And then it has to be differentiable and things like that. But the defining characteristics to me are input and output, because that's really what defines your task. Semantic segmentation has a very particular output structure. Things like keypoint detection also have a very particular output structure, and I'll go into sort of examples of these. Then of course you've got your data set, bigger the better, right? The more data you have, the better you'll be able to do that optimization, and the better your performance will typically be in the end. And then you have an optimization algorithm, which is based on the values of your objective. How do you decide what your new parameters should be? Your theta prime there, which you put in and repeat and repeat and repeat for quite a long time, and a lot of time in deep neural networks. You have to train for, in some cases, weeks, months. I don't know if anyone's really reported on something for years, but parallelism hopefully avoids that. But with language models these days, who really knows? So deep learning works. I think probably people here won't need to be convinced, but over the past 10 years, we've just been blown away by how well deep neural networks do at finding the mapping between any input data and output data. So this is an example of a classification task called ImageNet. This is possibly the most famous task in computer vision, at least. It's called image recognition, right, which is classification of images. So for any given image, you're trying to automatically decide whether it falls into one of a set number of bins. And in ImageNet's case, that's 1,000 bins. And the bins are anything from like jack-o'-lantern to hatchet or holster or tree frog, everyday things that you could potentially take an image of. And this is the top 5 error rate that's being shown on this graph. And in 2011, we started at like a 26% top 5 error rate. So you have to understand that deep neural networks produce sort of a confidence for each class or each potential output. So a deep neural network trained on ImageNet will produce 1,000 numbers. And usually you take the highest one and you call that the decision of the deep neural network. You can kind of think of those 1,000 numbers as confidences. They sum to one, so some people like to call them probabilities. They're not really probabilities, but they're confidences. So you take the top one, but in ImageNet, because it's such a hard problem, there's 1,000 different classes, you usually look at the top 5. And if the correct class is in the top 5, then you call it a good classification. So it was 26% in 2011, which was not based on deep neural networks. And then in 2012, AlexNet came along, which was Alex Krzyzewski and Jeffrey Hinton in Toronto. And it was sort of the first deep neural network that worked on a large scale. They sort of wired 2 GPUs together. It was a lot harder back in those days. And they managed to train one of these convolutional neural networks to do this task. And convolutional neural networks were not new. They'd been around since probably the 80s. I think that's when LeCun was doing his work, but it hadn't worked on large scale images, at least not high resolution ones until now. And you can see, I mean, the difference between 26% and 16% is huge when you consider, and this isn't shown, it had been hovering around 26, between 26 and like 32, I think, for 2 or 3 years before that. So this was a huge dip. And then using deep neural networks and based on this work, it just got bigger and bigger every year. I mean, the performance, people were starting to wonder, you know, when's it going to stop? And actually, a graduate student at Stanford in 2014, 2015 came along and actually did the task himself. He went through and tried to classify the images. He gave sort of his 5 best guesses for each image. And he had a 5% top 5 error rate. And in 2015, 2016, and you know, now it's just very commonplace that we can train deep neural networks to do even better than Andre Karpathy did, who I think now is the director of self-driving or deep learning or some sort of title like that at Tesla. So, you know, it works. I think we can all be on the same page that we can learn this mapping really well. And not just for this sort of standard task of classification, we can also do things like classification and localization, where we produce that same vector of probabilities, but then for other numbers, the origin of the bounding box, as well as the height and width of that box, with the goal being to sort of encapsulate that object that we're looking for. And you can imagine there's a lot of practical reasons that you want to just not just classify the image, but also find the object within it. You could also do things like keypoint detection, where you have a set collection of points beforehand, which are sort of given by different colors here in this GIF. And all you're trying to do is predict the positions of those points for a given image. And as long as you can collect a bunch of examples of the image and where those points are, you can train a deep neural network to find that mapping. And it works really well, as you can see in this image. And even this is a few years old now. So this is also considered something like a solved problem. If you have enough data, you can get it to work really, really well. Semantic segmentation, this is one near and dear to me. Here, every pixel in the image is classified. So again, you know, it's defined based on the output structure. Your input structure hasn't changed, it's still an image, but now our output structure is the size of an image, but for every pixel we have 1,000 numbers, which correspond to that classification thing. We develop some sort of objective function which measures how well we're doing this, and then we optimize the parameters of our deep neural network, which all it has to do is produce something that's the correct shape, right? So here, you know, sidewalk is a color. I think it's this pink. Road is a sort of purplish here. Cars are blue. This train is a green. You know, this is also something where if you have enough data, you can usually get it to work pretty well. The problem with medical imaging, and you know, I keep saying these things are solved, so you know, why do we talk about it? In medical imaging, getting a lot of data is hard. So these things are still really hard problems. And not only that, but the data changes over time. We're getting better at medical imaging. We're collecting data that looks different than it used to. So we have to be continually collecting new data and new data sets and training. So we'll get into all that in the future. Object detection. So this is a big leap. It may not seem like one. Now you have more than one box, but this time the number of boxes is a variable. We don't know how many objects are going to show up in the image. This is much more realistic, right? Because when we start looking at an image, we don't know a priori how many sort of objects we're going to be looking for. We have to make that decision. So here, I'm not going to get into it too much because it gets a little complex, but you can do things like put a grid pattern over the image and then classify within each of those grids, or look for a single box within each of those grids, and you can do that at different scales, have sort of confidences and then rule-based methods to sort of put those grids together into single boxes. That's something called single-shot detection. You can also do things like recurrent neural networks, which produce a new box at each iteration and then decide when to stop. So there's a lot of different methods that have been proposed. And again, if you have enough data, it tends to work pretty well. Instance segmentation. So now we're getting into sort of chaining these methods together. So not only are we doing this object detection from before, but then within each box, we're doing semantic segmentation. So even though these all have the same semantic class of car, they're labeled as different colors to represent the different instances of car in the image. And so KITS, which was mentioned, it was a semantic segmentation challenge, but we got the question a lot of why didn't you do instance segmentation here? Because there could be more than one instance of tumor. In that case, it didn't quite make sense to do instance segmentation because we don't always know what is a different instance of tumor. If you have two tumors that just happen to start growing right next to each other, they're going to grow into sort of one big sort of weirdly shaped mass, which in the image, we definitely can't tell if that's one or two tumors. And even the pathologist, after he gets it under the microscope, will just see a mix of sort of different types of cells. Just trying to find the border between those will be basically impossible. So we went with segmentation because it was more feasible at the time, but instance segmentation is something that we're exploring. And for things like kidneys, maybe it makes a little more sense. So in the 2021 version, maybe that's what we'll do. So instance key point detection, this is the same thing. You have your bounding boxes around people in this case, and then you decide on the key points that you want to locate within each of those people. And then finally, I'm going to talk about image super resolution, which is a sort of an interesting one. This is actually coming into medical image analysis a little bit because people are trying to use this with like low resolution CT scans or low dose CT scans. But here, this is actually one of the easiest problems to find training data for. What you do is you start with a really high resolution image, and then you downsample to a low resolution and try to train a deep neural network to produce the high resolution image based on the low resolution. So that's this arrow that says pulse under it. This is a 2020 CVPR paper. CVPR is sort of the top computer vision conference. And you can see the results are really good, right? You start with this really pixelated low resolution image, and then you produce something that's very high resolution and very believable, right? GANs are something else that they don't start with anything. They don't start with any low resolution reference or anything like that, just sort of a random latent vector, and then they can produce an image too that kind of looks like this, but that's sort of a different story. So this is supervised learning. We're just starting with, we have pairs and we're learning a mapping between them. All right. So that's my background on deep learning. I think for the purposes of what I'm going to go on to discuss, it'll be sufficient. Obviously, there's a lot missing, but that's outside of the scope, I think, for this time. All right. So question one that I think is interesting: how do we choose or design the best neural networks? It kind of sounds like this should be easy, right? There's a flood of papers about deep learning right now. I mentioned CVPR before. This is the number of submissions that CVPR gets every year, starting in 1990. The conference is actually older than that, but that's just how far I decided to go back and collect data. Clearly, there's a trend here, right? Looks, exponential or kind of like a hockey stick. It's growing and it doesn't seem to be stopping. So there's a flood of papers. There's a flood of people that are writing about how to do deep learning well. And it's not just papers in the computer vision literature. These are a bunch of clinical abstracts or clinical meetings. The AUA is the urology meeting, ASCO is the cancer meeting, or one of them, AACR is another one, RSNA is the radiology meeting. And this is the number of abstracts. I just did like a keyword search over all the abstracts for machine learning. And you can see again, I mean, it almost coincides with the sort of hockey stick here. There's a lot of people that are starting to use this stuff in medical imaging. So you'd think, and actually I forgot to mention this one, radiology, or RSNA, sorry, the Radiological Society now actually has a journal called the Radiology Artificial Intelligence. And it looks pretty good, actually. I've seen, they publish like 2 or 3 articles a month, so not a big high volume journal, but they usually publish good stuff. So there's a ton of papers. There's a ton of people writing about this. Why isn't it easy to see, what the best methods are? Hopefully, everyone is reporting that they have a good method, right? Well, the problem is the evidence. Even though there's a flood of papers, the evidence is just a trickle. You get a lot of sort of tables like this in images that have a single number for different tasks. So I cut that off there. Here's another one. You have a single number for each task. This is a single task here, validation percentage. Here's another one. You've got your methods and then your accuracy, your IOU. So, okay, they went with 2 metrics there. MSE, that's a different metric. But still, what's missing from these, here's another one, is anything that resembles rigorous science. These are point estimates. These are means. There's no significance. There's no confidence interval. And I think it's sad because the information is there to compute those things. And it would help so much to have them. This is, comparing one method to previous methods, and they're saying, okay, my loss function is lower, and that's a good thing. But if the confidence intervals overlap, then we don't have evidence to say with, the agreed upon scientific, standard of we have evidence for this, that this is actually better. And, there's so much of these papers coming in that we sort of have to synthesize between papers to come up with that sort of level of evidence. And so papers don't go as far as they would if these things were included. And it's just this really stubborn standard that people started by including just tables like this, and people haven't gotten away from it. So I think in terms of how to best choose the model, let's write papers that have confidence intervals and p-values for one thing. But there's more problems than that. Homemade baselines, and what I mean by that is things like these top 3 columns, or sorry, these top 3 rows in this table. So these are prior work. They've cited the paper that they're looking at. And in this case, they re-implemented these baselines. These are, deep neural networks that had been proposed, looks like in 2014, 2018. They rewrote them in their own code, and then they computed the performance on their own data set, and then they wrote their own method, and then they computed the performance of their own method on their own data set. And they found it was better, right? But unfortunately, it's just so easy. There's so many decisions. There's so many sort of quirks to training a model that you can botch it so easily without even realizing it. I'm not saying they're trying to sort of misrepresent how well other methods perform. It's just, one little thing and the performance can be lower than it should be. So tables like this, I just have a really hard time, accepting any sort of evidence of something being superior. And the discussions of superiority, like I said, they're not nuanced. There's no p-values. There's no statistical significance. There was this great paper in, I guess, 2005 from Johnny Anitas. And his recent comments about COVID notwithstanding, this is a very good paper about why most published research findings are false, at least in medicine at the time. And I think we're sort of coming on a similar moment in machine learning. I think why most published machine learning papers are not better than the baselines, something like that. Because these problems are just so pervasive. Here they were talking about p-hacking, and that's even more malicious than I think what's going on here. So how do we solve this? Well, people say, well, we release our code, so clearly it's reproducible, right? But with models as big as they are these days, and I like to pick on language models here because they've just gotten so ridiculously big, retraining GPT-3, which is OpenAI's most recent language model, would cost $4.6 million on a Tesla V100 cluster, which the average person does not have. So just releasing your code here does not mean that your results are reproducible by any sort of reasonable standard. Okay. Benchmarks. So this is a better step in the direction of fixing this. So here, instead of using their own data, which is typically what happens in tables like this, you use the same data set. So if someone's nice enough to release a data set to the public. ImageNet is one instance of that. Coco is a data set that was released by Microsoft. So this data is made available to everyone. Everyone trains their model on the data, and hopefully there's some agreed upon test data that people also use to get their objective measure of model performance. This is a lot better because your comparisons of the test data, number one, don't depend on re-implementing someone else's baseline, which is sometimes not feasible. And even if it's feasible, it's not usually easy. Here you're using just their published results. So usually you can hopefully trust those. And it's a much more fair comparison, and the comparisons have more statistical power because you can use paired versus unpaired statistical tests if we could get people to use those at all. But this is still based on trust because you're still expecting people, you're still relying on people to report results fairly, report their performance measures fairly. So what I think we really need to do, and I'm a huge proponent of these, is challenges, which I think resolves almost all of the problems. Challenges, and KITS was an example of this, and it was already mentioned, but I'll rehash what they are. In a challenge, there's a set of organizers which release a public data set for training, but then keep a secret set of testing data to themselves. And they manage that so that when people submit their methods, they can run the methods over the test data and give them a number back. And hopefully they don't even just give it to the person who made the submission, they publish it somewhere. So there's a record of this person looked at the test data or didn't look at it, but evaluated their model in the test data at this time. And then, this goes on for a certain amount of time. A lot of times there's a deadline to the challenge. And then after that deadline, a leaderboard is announced. And then, the top of the leaderboard at that time gets a prize. In our case, it was, something like $5,000. So nobody's supporting themselves based on winning challenges, but it's a little bit of a carrot to get people to participate. And once challenges are retired, maybe after the leaderboard announcement, or maybe leaderboard announcement plus 2 years or something, you can release all the data and then it becomes a benchmark, which is still a lot better than what was there before. So in this case, it's sort of trust-free, except you have to trust the organizers, but usually they're incentivized to act in good faith. Everything is centrally managed. So, you know that everything is reported. People aren't fine tuning on the test set because you'd see that. You'd see their submissions showing up there often. So with KITS 19, we had something like 100 teams submit to what we call the official challenge period, which was like a 2-week period where people could submit their methods, we'd run them, we'd compute the results and put it on a leaderboard. But we wouldn't show anyone the leaderboard until the submission period was up. So nobody could submit more than once knowing what they got in the past. So we had about 100 teams submit during that time. So this little trophy here is showing the number of teams that have submitted. We're still managing that leaderboard. We're still allowing people to submit, but they don't go on the official leaderboard anymore. So 778 submissions have been made since the official deadline, which was last July, I think. So clearly there's a lot of interest. I think it's sort of a win-win because people from the more medical side of the research can use this to really quickly evaluate the state of the art on a particular segmentation or classification or keypoint detection or whatever task. And they don't have to bring the expertise. And then other people bring the expertise and they get a really good data set that they get, an awesome, trustworthy way to report their results on. And then the methods that actually work well will float to the top and get recognized like they actually deserve to. Whereas right now, it's just really hard to sift through all the papers and try to synthesize evidence to come up with what methods actually work the best. And I think that a good case study here is something called NewNet or NNUNet. And so this is a method that was created by this guy named Fabian Eisensee, I think his last name is, from the German Cancer Research Center. And what he did was he focused on all the decisions sort of around the pre-processing of the medical imaging before it goes into the deep neural network, rather than trying to create all these like architectural garnishes, like residual connections, or like, what's it called, the attention mechanisms that people come up with. And sometimes people have these like recursive areas within it or different branches. He just used standard UNet with a few residual blocks. So that was a very standard thing to use at the time. And he just focused on sort of what numbers do I use to sort of scale the input data and normalize it, and how do I resample it so you can sort of stretch the images or compress them. He did some meta learning on what parameters to use for that part and just used a very out of the box model. And this was a very taboo idea at the time. So people didn't think that the pre-processing stuff was very important. And then he went on to sort of dominate all of the challenges in 2019, even though his original paper about this was rejected from MICAI, which is the standard sort of medical image computing conference. And so what I'm showing here on the right is a bunch of different challenges. Kits, if you're interested, is these two right here. He broke up kidney and tumor into two different things. All the blue dots are other people that have submitted to these challenges, and the red dot is the performance of his method. Very clearly a trend here, right? He's at the top of every single challenge, or at least near the top. So to me, this is very strong evidence that this method actually works in the real world. But you know, it really shows how hard of a time people are having finding what is actually good evidence for something working when his paper was rejected from MICAI, even though it clearly works. So I think challenges are the future. I plan to keep hosting challenges as long as I can, I guess. We did it in 2019. It's quite a lot of work to do, but it's just so it's so rewarding to see that the evidence really comes out about what actually works, and the people who deserve it really get recognized. But of course, you know, as a challenge organizer, there's a lot that falls on you to make sure that what you're reporting is stable. So, you know, all that statistical significance, you really have to do that yourself. So here's a map of p-values. This is sort of a common way to visualize the significance of difference in rankings in challenge results. So on the y-axis, you can think of this as the first team that you want to compare, and on the x-axis, the second team that you want to compare. And the second team ranked lower than the first team. That's why we've got nothing below the diagonal here. And then what's colored here is the p-value of that comparison. And you can see NewNet is way up here at the beginning. It scored first, and it's statistically significantly higher than all but the second place team. So pretty strong evidence, in my opinion. All right. So that is the end of question 1. Now, question 2, what do we do about imperfect data? There's a lot of people, especially in semantic segmentation, that would like to believe that all of the data that they create and release is completely flawless, there are no errors, and people should just take it as being ground truth. That is not the case. Imperfect data exists. There is absolutely no way around it. No matter how careful you are, there's always 1 or 2 voxels out of line, and usually there's many more than that. So in medical imaging, this is like very pronounced. And it's very visible because in cross-sectional imaging, at least, so things like CT scans or MRIs where you have a third plane, usually the semantic segmentation labels are done in axial. So that's sort of taking a cut out of view that would be parallel to sort of the, I don't know, how do I say this? It's easier to draw it. I don't know why I'm struggling with this so much. Axial plane, it would go through both of your eyes to the back of your head. Good enough. So usually the delineations are done in that axial plane. So you draw sort of a circle around this. It looks nice and smooth, looks like you got everything. But then as soon as you turn sort of the whole block of labels on its side, and you take like a sagittal cut or a coronal cut, you can see how they don't line up. In this case, you can see, you know, there was a whole gap between one slice and the next slice. And, you know, brain tumors don't look like this. Brain tumors look kind of weird. This is a brain tumor data set, but they don't have weird discontinuities in them like this. This is a pancreas segmentation data set. Pancreas don't look like this either. So you can see really well that there are problems in your segmentation, no matter how good they look in the axial plane. So it stands to reason that there are problems in data that isn't medical data too, like the problems in the semantic segmentation data sets that are used for self-driving cars and, you know, all sorts of other applications to real world data. And there's 2 types of errors, at least this is the way I like to break it up. There's biased errors and unbiased errors. So biased errors are errors of intention. So if you were to annotate the same feature 1,000 times and take the average of all of your annotations, it would still be wrong because you were intentionally annotating something that turned out to be wrong. So even though there might be noise that would average out, that error of intention would show up in the average of all your annotations. In unbiased data, the average would be perfect. You had the right intentions with everything that you were drawing, and all the noise would average out. So the unbiased errors are really just that coloring outside of the lines, the things that would average out the limit. So biased errors can be mitigated by just having more knowledge about what different regions are in the image. So usually to be totally unbiased, you have to be an expert medical professional with lots of training. It's great to have radiologists on the team because they can help a lot with this. But to be unbiased, you need to have a lot of free time because to be low in unbiased errors, you need to have a lot of free time. You need to be able to be very tedious or very meticulous in the way that you're annotating your regions, and you need to be willing to go back and erase if you colored outside the lines a little bit. It's very time consuming to have 0 unbiased errors. So the question becomes, okay, how much do these errors matter? And the answer is it depends. So if they're randomly distributed, it turns out deep neural networks are really resilient to this label noise. If your errors are sort of anywhere in the image in semantic segmentation, or if you're doing classification and just like a random spattering of your data happens to be mislabeled, the deep neural network will learn through that basically no problem. You won't even see a dip in performance. But unfortunately, this is really unrealistic. Especially in segmentation, all of the errors will lie on the region boundaries, which coincidentally are the hardest region or the hardest area of the image to label correctly for the deep neural networks as well. So the errors that show up on those region borders will really hurt the segmentation performance. So we set out to sort of quantify how much this affects it. And so we induced errors artificially. We started with a liver data set, which we're representing just as circles for this demonstration. And we introduced 3 different types of errors for our experiment. One we called smooth errors. So we sort of did an interpolated spline on random key points around a contour. So you can see as we go down in the agreement between any 2 scans, the amount of deformity on our circle goes up. And then here we sort of artificially induced what it would be to stack the errors from, the slices from this type of error together on top of each other and look at them from the side, as I was saying. So then it looks kind of choppy like this. And then third, we just had this unrealistic case of the errors being totally randomly distributed throughout the image. And then we trained deep neural networks and then of course tested them just on the perfect data. So what we found is that the choppy versus smooth, so that was that second column versus that third column, had basically no difference. But there was a significant difference between the border localized errors, so these 2, and this third class of the unrealistic case. So that's this one here. So the performance is clumped up here very high. And in the other border localized errors, the performance goes down a lot with the higher error rate that you've introduced. So this shows that segmentation, at least, is unique, that these errors are on the border and they're really pernicious there. And we can theorize that errors in a classification setting will also be on the borders because those are the harder ones to classify. If you have many raters, they're probably going to have some bias. They're going to be subject to some number of biased errors. And those are going to occur in the cases that are already the hardest for the deep neural network to learn to classify. And so this sort of same thing will show up there, but that's much harder to study. So errors have an effect, was sort of the result of this. By the way, I really regret the way that I visualized this data. They say your PhD is like one long group project, but your partner is you 3 years ago and they don't respond to emails. That's the way I feel about this because I really should have visualized this a lot better, but that person is not responding to emails anymore. All right, so what do we do about errors? They're a problem, but how do we get rid of them? So I think at the very least, we need to estimate their prevalence. So people keep releasing data sets and not having any sort of idea of how many errors they contain. So what I think the bare minimum you need to do is release a data set with some proportion of it, like 10% of it, annotated twice. And then you report the incidence of errors on that 10% that you have 2 labels. At the very least, that will give you some sort of hard ceiling on what the test set performance will look like, right? Because if there's 20% errors in your data set, you probably don't want your network to be learning to be wrong 20% of the time. That just happens to coincide with the 20% that are wrong in the test set, right? So if you have 20% errors, you're never going to get above 80% performance. At least you hope not. And then you should aggressively address bias, because biases can be passed on to the deep neural network. It will learn how to do the things that you consistently do. So, you know, there needs to be lots of training and lots of checks to find things that were intentionally annotated incorrectly. You should thoroughly document your annotation protocols and instructions, because if you ever want to update your data set later and there's new people that are working on it, they need to know how you did it before, so that this new data that you're annotating isn't totally different. That's another weird case of errors that would be interesting to study. And then consider helpers like thresholds or superpixels. Superpixels being sort of globs in the image that are visually similar to each other and make for sort of good ways to cluster pixels together. But you need to be careful if you do this, because they can introduce bias, right? So what we did in kits, and actually I'm very proud of an image like this, because this is a coronal view of data that was annotated in the axial plane. So if we were bad, you would see lots of choppiness here. But actually it looks very smooth. It looks like the region very nicely lines up with the border of the kidney. The tumor, you can see, is a little bit ragged on that boundary with the kidney. And you get that because that's the hardest thing to annotate in this image. Everything else you can actually do with a threshold. Because the area that's outside of the kidney and the area that's outside of the tumor, as long as it's not kidney, is adipose tissue almost all the time. Sometimes the tumor will about the psoas or the higher up in the kidney, sometimes will too. But for the most part, at least in Americans, where we have, you know, that big layer of visceral fat here, you have this very dark adipose tissue, which has well-defined Hounsfield unit ranges. Hounsfield units are the intensity that shows up in CT scans. It's always going to be at least less than -30, if not much lower than that, where kidney is almost never below like 20. So you have a nice separation there, and you can call any sort of boundary that you draw that's outside, that includes sort of very low attenuating tissue. You can just remove the low attenuating tissue with a threshold. So we use that helper, but we know that there's a well-defined physiological reason to use that helper, so we can be confident that we didn't introduce any biases we don't like. So the other thing that I think you can do about errors is you can sort of break up the work. This is something we're piloting for KITS 21, which is the KITS challenge that we're hosting next year, and I'm gonna try to do a live demo of this. Hopefully it doesn't fall to pieces on me. So this is the platform that we made to annotate data for KITS 21. I'm going to show you guidance on a tumor region. So basically what we're doing is going in and putting these yellow pins in, which hopefully make it totally unambiguous to even a non-expert where the tumor should be and where they should draw their delineation if they were to come in and do this in the future. So that's the guidance part, and we do that all the way through sort of the region of the tumor. And then we're actually going to ship this to Mechanical Turk, and we're going to have them come on and do these sorts of delineation. And this one's not perfect. It's including some outside stuff, so I can go and fix this. So what they're doing is hopefully drawing along this border. As I said, this is the hardest part. And then excluding things that are too bright to be adipose. And save, see how that looks. Server might be busy right now. It's gonna think for a while. That's why you don't do live demos. Cool. So we're gonna try this out. I think it's sort of the best of both worlds, right? Because we have experts that are going through and doing this guidance, but it's not very tedious, it's not very time consuming. And then we have people who have all sorts of time on their hands and are willing to work for pay, who will go on and do that delineation, which can be very tedious. So we'll see how that works. Hopefully what this will do is we can do the guidance once, and then we can get many segmentations for each case based on that guidance, because the segmentations actually become the less expensive part of it. So then if you have multiple cases, you can use things like simple or staple to put them together. Those are just sort of averaging or aggregation methods. Or you can just release all of them together and let the participants of the challenge decide what they want to do with multiple labels that might be conflicting in different ways. But regardless, it's going to be interesting for the evaluation phase, because we can see sort of if networks are worse in areas that tend to show high disagreement in the multiple labels that we have. And I think they probably will. So we're working on trying to come up with a metric that penalizes people less if they get areas wrong that humans also tend to get wrong, which seems more fair to me and sort of a better way to evaluate the performance of a segmentation network. So the last thing that I think we should do about errors is study them. It's sort of a not very sensational topic to look at, labeling data and how to create good data sets for machine learning. But it's an extremely practical one. I think it's something that we should be studying in sort of a more scientific and rigorous way. But if you try to write papers about it and send them to the top machine learning conferences, they'll reject them out of hand because they don't think they're very interesting or sensational. So what we did is we created a workshop, and this is in association with MICAI every year, called Labels, which is Large-Scale Annotation of Biomedical Data and Expert Label Synthesis. And we accept all sorts of very practical, not very flashy papers that are all about sort of, hands dirty, how do we make labels for medical data that are very high quality without using many resources. And I have a lot of fun organizing this every year. I think it's a great event for something that doesn't get talked about enough. All right. Question 3, and I promise my answers get shorter over time. So how important is transparency? You hear it all the time that black boxes are not going to be accepted in the medical community. There's a lot of people who think that. If you have a deep neural network and it takes an input and produces an output by some sort of mysterious process, which is how clinicians think about it, it does seem mysterious to them, then why should we trust it? Or, how can we be sure that it's not doing something devious or, I don't know. So people have, really pushed for these sorts of methods that they call interpretable deep learning. And usually they take the form of something like this, where you have your input image, and you have some sort of method to come up with a heat map over what was important in that input image, what the deep neural network sort of looked at when it was making its classification or segmentation or what have you. In these cases, we're talking about just classification. And, in concession to them, they look very pretty, right? Like seeing this is very reassuring. It's like, okay, that's great. The neural network is actually looking at the dog rather than the background when it's deciding that this image is in fact a dog. I think it becomes less clear in this case on the right, but they certainly look pretty, right? Dome is concentrated here on the dome, so I guess that's good. So I think that, it's theoretically interesting work. I have a hard time seeing the practicality of something like this. I think it's really easy to come up with pretty pictures and come up with a story for yourself of why it's making that classification or how that heat map sort of makes sense for that class that we're talking about. And you can do even more crazy stuff. Like here's an example from Google, and this got a lot of press many years back, called Deep Dream. And this is where you sort of you change the actual image itself in order to produce a maximum value at some point throughout the network, whether it's at the end of the network, so you're trying to maximize a certain class, or confidence in a certain class, I should say, or it can be some like intermediary in the network if you want to say, okay, I want to maximize this neuron at this position. And the image sort of contorts in all sorts of ways to make that happen. And you know, it's very interesting. It's very visually interesting to look at. But again, I don't know what concrete things you can deduce from looking at an image like this, other than, oh, that looks pretty. But we set out to try to make these things work for us. In this project, I was working with a pathologist. These are the people that look at tissue under microscopes and decide, you know, this is cancer or this is not cancer, or this is, you know, interstitial lung disease versus pneumonia or something. So, you know, they're sort of considered the gold standard in medicine. If the pathologist says it's something, then it's really something. The radiologist, you know, they make a joke that radiologists always say correlate clinically, because they're not really sure a lot of the time, but pathologists are almost always sure. Because they can see the tissue in all its glory. They can stain it in all sorts of ways. They can do all sorts of immunohistochemistry on it to see, you know, what immune cells or antibodies are there. You know, they have all sorts of tricks. So they're very close to the actual underlying biology of medicine. So what we thought would be interesting is we have these two cases here. This is lymph tissue near the breast. And the case on the right is breast cancer that metastasized to the lymph node in this case. And on the left, we have healthy tissue. So, you know, we can train an out-of-the-box deep neural network to do classification on patches of this tissue to decide whether it's cancer tissue or healthy tissue. And then what we thought is, okay, let's try to look at these saliency maps and see how the deep neural network decided that a particular image was cancer or healthy. And maybe it'll learn something that we don't already know. You know, maybe we can actually use this to discover something we didn't know about biology, because the deep neural network found it as sort of the path of least resistance to do this classification accurately. So what I did, and I can do another brief live demo here, I made this little website for the pathologist to have a look at. And basically it's got a whole bunch of images, like probably close to 1,000. And for each image, it's got the heat map that the deep neural network, that we generated based on the deep neural network doing its classification. And it's also got the classification that the network had and the confidence that it had. So that's that value where they all add up to 1. So this one was very highly confident to be malignant. It is in fact malignant tissue. And this is its heat map. And you know, I'm just looking through these. I'm not sure this is a great example of it. I guess it kind of is. So the pathologist looked at these for a while, and then he called me one day and he was all excited because he thought he had found a trend. He thought he saw that the heat in our heat maps was always very concentrated on the cytoplasm of the cells rather than the nuclei. The nuclei are those sort of darker features here. But he found more of the heat is sort of in the cytoplasm, especially the cytoplasm that's adjacent to the nuclei. And he thought he had a reason for that. He thought of a biological mechanism that this cancer might be not only changing the appearance of the perinuclear cytoplasm, but also the color of it. He was very adamant that he thinks the color is changing and the network was picking up on it. So we thought, okay, cool. Let's formulate this as a statistical test, right? There's a saying like, you know, in God we trust, but for all others we need data. So we went through and we segmented the nuclei in all of these cases, and we counted the amount of heat that was within the nuclei and outside of the nuclei based on what we would expect based on just the relative prevalence of nuclei versus cytoplasm in the image. And we did that again after retraining without color. And we thought, okay, if this is really the case, then the amount of attention in the nuclei for the gray images will be much higher than the amount of attention in the nuclei in the colored images, because here in the colored images, it's looking outside of the nuclei. And lo and behold, that's what happened. The results were significant, and it looked like deep neural networks like colored cytoplasm when they're making that classification. So we were very excited at this, and you know, we submitted it to USCAP, which is the big pathology meeting every year, and they gave us a nice a platform talk, and everyone was very excited there. And then, you know, I came back and started to write this up as a journal paper, and I thought, okay, it'd be good if we used a different method to get at that attention. or where the deep neural network was looking, just to make sure that, that lines up too. But I didn't really think, I'm sure it will, right? And it turns out the results were also significant, but in the opposite direction. So here we used ablation. So we went through and we sort of slid a gray box over the image, and we recorded how much the predictive confidence went down when the box was in each given position. And then that sort of went into a weighted sum for the pixels that made up that box. And then you get a heat map. It's very similar to doing saliency maps, which was the first method that we used, and that's a gradient-based method. But this time you don't need to use gradients, you sort of approximate them in this way. So this was very discouraging. That it depends, if you use another method, which should be getting at the exact same thing, you have exactly the opposite results. So that's sort of what has me down in the dumps about methods like this. I think they're very pretty and very interesting, and potentially we can learn things about even biology by using them, but we need to be very careful. Each interpretable deep learning method is asking a very specific question, and that may or may not line up with what you actually want to know for a given case. And beyond that, with so much visual information, the setting is just a breeding ground for confirmation bias. You can come up with an exciting story no matter what you're looking at. So this is another case. This is called predictive difference analysis, and this also turns up very interesting and compelling arguments for classifying this as, I don't even remember what type of bird. But again, it's if you use something else, it would probably look totally different. But they are pretty, so that's the one thing I will concede. But what I will say is transparency is not all bad. I think we will need to accept black boxes eventually, and it's not just images. There's things like polygenic risk scores, which are becoming a big deal in cancer, that people are accepting, and they're totally black boxes. Like, you can't even look at the image in those cases. You can just look at DNA base pairs. But here, at least you can look at the image. And I think a good bridge to that would be radiomics, which is the setting where you do semantic segmentation first, usually. Sometimes you don't have to, but almost always you do. And then you extract some feature from the image based on that segmentation. Here I'm extracting texture. So this is a renal tumor segmentation, and then I'm running a Laplacian of Gaussian filter over the voxels inside of the tumor. Some areas are lighting up, others are dimming down. I take a histogram of the response values of that filter, and then I look at the width, basically, of the histogram. I think I'm doing standard deviation. And that's the value that you get out. And in this case, that value actually correlates pretty strongly with the subtype of tumor. Clear cell RCCs are a lot more texturous, I guess, if that's a word. And so they have much wider histograms in this case. And so I think we can be reassured by something like this. Even though the segmentation is totally a black box, at least we can look at the segmentation that came out and say, yes, that's a good segmentation, or no, that's not a good segmentation. So really the deep neural network is just acting as a time saver, but that's not nothing in this case. And I think, these values are not something that would be clinically feasible to get at point of care without automatic segmentation. So, this might not be as predictive as something like a deep neural network, but it's still not bad. And like I said, I think it's a good bridge. This is another one that we came up with based on segmentation that's looking at the, I wish I could make that go away. That's looking at the boundary hardness, we're calling it. So this is like a really fuzzy boundary between the tumor and the kidney, where this is a really hard boundary. So basically what we're doing here, segmenting the tumor and looking at the average directional derivative of the image over the boundary between the tumor and the kidney. So this has a value of 30.7, this has a value of 64.3, this is a value of 88.4, this is 103.8. So it matches up really nicely with what we can actually observe, ourselves. But we can compute this value with really high precision and plug it into things like logistic regression models, which have been used for eons in medical statistics. All right, that's the end of question 3. Question 4, how do we find uncertainty and what do we do about it? My answer is fairly short here because I realized how many slides I was writing for this presentation and I wanted to keep it under an hour. But I couldn't do this presentation and not mention uncertainty since it's such a hot topic right now in medical imaging. So there's many proposed methods that, you know, for time reasons, I'm not going to get a lot into, but there's a lot of methods for uncertainty quantification. The one that seems most popular to me, and this is just my impression, is Monte Carlo dropout. And this was, you know, all of Yarngall's thesis. If you keep up with this space much, you probably have heard Yarngall's name here and there. And you know, he showed pretty convincingly that if you do dropout, which is just a standard regularization technique where you just basically cut off neurons in the network and not let information flow out of them for certain passes, and you randomly decide which ones this happens to according to some prior probability rate, and your output will be slightly different in those cases. And you do that a bunch of times and your output is going to take some distribution, and that distribution can be thought of as the posterior if you were to have a fully Bayesian neural network. At least that's a decent approximation, hopefully, to that. Other things, you could train a bunch of models and average them together. You can also combine those two, so you can train a bunch of models and then run Monte Carlo dropout on all of them and then average the posteriors together. You can use quantile regression, which is just sort of an explicit calibration technique for uncertainty. Or you can try to do that Bayesian neural network thing, which people seem to have been working on for a very long time and not getting very far. I don't follow that space a ton, but obviously, you know, it's something like n cubed, I think, computations to do fully Bayesian neural networks, and with networks having, you know, billions of parameters these days, I don't think that's ever going to be possible. But people seem to have good ways to approximate it. So regardless, you get some probability value out. And how do you decide whether the probability value is good? Calibration plots are the answer, or at least my opinion. Calibration plots are the most convincing way to show that your uncertainties are actually good and useful. So what you do here is you break your predictions into bins, where you have a bin from 0% to 10% predicted probability, 10% to 20%, 20% to 30, 30 to 40, and so on. Looks like their bins might have been slightly different from this. But then what you do is you look at the true values within each of those bins. So the proportion of correct values, or not correct, the proportion of positive values within each of those should lie on the diagonal to that X value that you started at. Just based on, you know, the definition of well-calibrated probabilities, right? If you predict something has a 20% chance of being wrong, then you'd expect that 20% of the cases that you predicted 20% would be wrong should be wrong, right? So if you have a probability plot or a calibration plot like this, and this is a really good one that lines up, I'm going to trust the values that your network is predicting. So then the question becomes, what do you do with it? So first we have to convince people to show these things, and a lot of times people don't in the literature right now, because generally with deep neural networks, if you don't make a concerted effort to make them have well-calibrated uncertainties, this won't look good at all. Deep neural networks tend to be really confident even when they're wrong. But okay, assuming we have well-calibrated probabilities, what do we do with it? And this is something that, for some reason, it's a really heated debate. There are some people who really believe that we shouldn't hand raw probability values to clinicians. And they cite all sorts of literature in psychology and I don't know what other fields, probably just psychology, which shows that people are really bad at interpreting probability values, especially if the stakes are high. People just in general don't have a good intuitive sense of the difference between 20 and 30%, even if academically they can understand it really well. I'm in the other camp. I think we should be handing raw probability values to clinicians because it's more information, and clinicians in general are really good at doing evidence-based medicine and coming up with ways to handle values. They look at, you know, continuous values all the time, like test scores. or I shouldn't say scores, I guess test results, EGFR values, things like that. Lab values, that's what I mean to say. So these are not new concepts to clinicians, and we should be giving them all the information rather than just saying yes or no. You know, people might say, okay, you should have some portion that you just reject and then it comes back on the clinician. But just the fact that it was so uncertain that you thought reject is also informative to the clinician and the patient as they do shared decision making. So I really believe that the probability values should be out there. They should be viewed by all, and you know, they should be handled carefully. But we shouldn't try to hide them, I don't think, behind just like discrete predictions. All right, fifth question. Looks like I have 5 minutes left to at least to 7:20, so that's good, because this one's very short. When is a model ready for the clinic? So okay, we've trained our deep neural network. It's making great predictions. It has well-calibrated uncertainties. Maybe you know, you have all sorts of evidence that your model makes good predictions. I strongly believe, and I feel very strongly about this, that we need to do randomized trials. Just the fact that you have great accuracy doesn't mean that your model is going to do good when it is put in a clinical scenario. The interaction between prediction models and humans that are in a medical setting or any other setting is very unpredictable. If you have an automatic, you know, radiology report generator, maybe it makes, maybe it does well in a controlled test where you have a radiologist supervising it, but in practice, radiologists might be getting lazy because the model works so well, and they'll sort of go on autopilot, and then they'll start to miss things that they didn't used to miss. And they were expected to catch, at least based on areas that maybe the model was weak. So, you know, this is very important, I think. We need to do randomized controls trials where you have your standard workflow that doesn't use AI. And, you know, when patients come in, you randomize them either to that standard workflow or to this new workflow that you're proposing. And then you need to measure a hard endpoint here, not, you know, accuracy or precision or recall or, you know, anything like that that can show up in just a controlled test. You need to have something that actually matters to the patient, like length of survival. Or, you know, pain relief, or something that the patient actually cares about. You know, it's just so important that we do this, and I see it almost none. And what really bothers me is that the FDA doesn't seem to be asking for this either. You know, I'm not an expert in approvals or anything like that. I just look at what comes out, and I see a lot of systems being approved based on 510K, which is that daisy chain thing. It's where you show that you're substantially similar to a system that was already approved. Of course, the system that was already approved could already have been shown to be substantially similar to something else that was substantially similar to something else. And all of a sudden you're going back to 1990 and you've got a system which finds the maximum of a single channel of an echocardiogram or something. And that's being claimed to be substantially similar to an AI system based on, you know, GPUs and a billion neurons. It's just ridiculous. And they're doing this based on, you know, retrospective data on 300 patients and, you know, just based on an accuracy soft endpoint or something. I don't know. I just think it's crazy. There was a recent case, and this got a lot of press. Google has a retinal image analysis system that's looking for evidence of diabetic retinopathy. That's the image that I have over here on the right. And they deployed it, I think, in Thailand. And they had way worse performance than they were expecting based on their controlled tests. And it's because there was this weird human factors thing where the way that they were capturing data and knowing that it was going into an AI system was totally different than the people at Google were expecting data to be coming in as. And it was just a nightmare for people who were using it because they didn't know if they could trust the results, because they could look at it and say, no, I think that's wrong. So, you know, we really need to have these dry runs, and I think it's much better if you have a control arm to make a fair comparison to. Yes. So beyond that, the first RCT is just the beginning. After your controlled trial, you need to observe these systems over time. It's, you know, things like really rare cases that would be hard to show in a randomized control trial, that, for instance, people with solitary kidney, which, you know, they have a single kidney instead of two, Maybe their segmentation performance is way worse and there's a hard endpoint that suffers because of that. That's not going to show up in a randomized trial because you only have a few hundred patients. Usually you're not powered to find a difference like that. But in the real world, in an observational study, you can look at Medicare data or the NHS data or something like that, and look for disparities that might have been introduced, like something like that. Or maybe people that are not on private insurance for some reason are getting scans at lower quality hospitals, and then that's reducing the segmentation performance, and then that's leading to a worse hard endpoint. But we need to be really vigilant in looking for these things because it's entirely plausible that they could happen. And if nobody looks for them, nobody's going to find them. And these things are just going to become ingrained in the next generation of systematic biases in healthcare, which already are pretty bad, right? That's very well documented right now. So the last thing I'd say, and this is something that I think Peter Chung told me. He's the director of the Center for AI and Diagnostic Medicine at UC Irvine. He said he thinks that models are going to be approved only for particular scanning models, and he thinks that they're going to be actually built into the hardware of scanners, because that's the only way to control what type of data the models are being run on. If you put it in the PACS system, which is sort of like the EHR system for images, people are going to be running the models on data that they shouldn't be run on. And I thought he was crazy at the time, but the more I think about this, the more I think he's right. We need to give very narrow approvals for systems, for models to be used on scanners which they were validated on, or maybe populations of scanners which they are validated on. But if you train a model and you validate it totally on a Siemens scanner, and then you run it on a Toshiba scanner, the performance is uniformly worse. We've shown this many, many times in the medical imaging literature. And it's the same for every pair of scanner brands: GE, Toshiba, everything else. I think there's only 4 that are big, but I think we really need to be narrow with our approvals and what type of data each model gets shown needs to be strictly regulated, and we should make those regulations, I guess, as explicit as possible. So I wouldn't be surprised at all if the norm becomes to wrap models with particular scanner hardware. All right, 7:20, look at that. I think I'm right on time. I'll start acknowledgements now. It should be short. I have to say that to do this work takes an enormous team from many different disciplines. We've got computer science here on the left. And then, we've got people from all over. We've got tons of medical students that work with us, and we're really lucky to have them. They always bring an interesting perspective and just a willingness to work hard. And, they're helping us to annotate all sorts of data for our next challenges and, the ancillary studies that we do for those. We've got some great faculty. Subodh Rajmi is a urologist, Ben Spilseth, the radiologist, Andrew Taylor, also a radiologist. My advisor is Nikos Papanikolaopoulos, and my co-advisor is Dr. Chris Waite, who just recently moved to the Cleveland Clinic. We were very sad to lose him, but he's in a good place now. And yeah, we've got some other undergraduates from really all over, just people who have contacted us looking for cool things to do. So yeah, I mean, huge thanks to everyone on this list, as well as, huge thanks to the people that give us money to do this work. So the ARCS Foundation, they gave me a very nice scholarship, and National Cancer Institute is really the main funder for the research that we do. Auris and Retina AI are funders of the labels workshop that we have every year. Climb for Kidney Cancer is a charity that tries to get people to be more active, because actually obesity is a huge risk factor for kidney cancer. And they've raised some money that they've donated to us to do research. And then Intuitive Surgical has given, they gave the $5,000 that was the prize for the Kids Challenge last year. So yeah, that is the end of my talk. So I think I'll keep sharing my screen in case there's questions, but what happens now, Eric? I'm not sure I can hear you.
Nick? Can
yes.
You hear? This is Daniel Feldman. Sorry, I don't know what happened with Eric's mic. As people have questions, you can just let us know in the chat and we'll unmute you, or you can unmute yourself. That's fine too. I just actually had a quick question to get the ball rolling.
Okay.
All the segmentation you presented was two-dimensional. Is anyone working on volumetric segmentation for medical images?
Yes. So actually, the KITS challenge is volumetric segmentation.
Oh, okay. I'm sorry. I
No.
completely misunderstood then.
Yeah, no, that's my fault. I should have made that more clear. So those are CT scans. And yeah, they are all visualized, I guess, as 2D. But I probably should have rendered a volume just to show you guys. So yeah, so the data was annotated in this case in the axial plane, which is perpendicular to this plane that we're looking at. And then it's being viewed, you know, in the coronal plane here.
Got it. Thanks. All right. If there are any more questions, there's plenty of time. So.
All right. So Nick, I have a question. So you talked about you seeing the future being the image collection being very specific to the OEM manufacturer, like a GE system having a specific image collection like protocol, and then like a Toshiba system having like a very specific and different image collection protocol to a GE system. So what do the healthcare professionals think about that? Do they like that approach, or they think maybe there's a way for these OEMs to standardize, you know, the part of the equipment? So like it's very common for like automotive OEMs to standardize one particular component of a vehicle. Do you think the medical equipment OEMs can do the same thing and help the industry that way?
That's a good question. I think it would be difficult. So the reason I say that is because, you know, we've seen studies where people will train a network and validate it on GE systems, and then they'll try to validate that same model on Toshiba systems, and the performance drops like 15%. So that would make me think, okay, we shouldn't be using that model on anything but GE systems. So one possibility is that, you know, you train a whole bunch of models, you train a single model on a whole bunch of data from many different manufacturers. And then hopefully it learns to be robust to this sort of difference. You know, there's a difference in the shape of the table, which shows up on the image. I wonder if I can show that here. Thought I had an axial slice. It's just below the image. So there's a metal table which lies under the patient, and that shows up in the image. And that's a different shape for each of the manufacturers. So that's a very visible difference in the images, which could be contributing to this sort of error. But there's also probably more subtle differences. You know, the way that the spiral in the CT goes around. I mean, I don't know. You kind of have to use your imagination to think about it, but it's sort of this weird phenomena that's kind of hard to explain. But like I said, you know, it's possible that people train a model based on data from many different manufacturers, and then it works on all of them. But then a next generation of scanners comes out. So now what, right? We have to revalidate, and if the performance is bad, we have to train a new model, you know? So, I mean, we can try to make it as consistent as possible, but at the same time, we don't want to be consistent because we want our scanners to be better and more sensitive in the future, right? Yeah, I'm not sure that the sort of consistency that we would need is possible, no matter how hard we try.
Okay. Any other questions for Nick? All right. So there's
I have a question.
Okay.
Hey, this is Mohsin from Indiana. So I have a question to Nick. So Nick, you talk about how we can interpret the result of classification, for example, using a deep neural network as a black box, for example. And you mentioned that it's okay actually to do LIME. For example, there is a LIME library or SHAP library to maybe show the area where how the classifier has learned how the classifier was like learning how to make difference between images. Mm-hmm. So if I ask you, like, what is the best method to use for interpreting the result, and what is the pros and cons for using such like libraries like SHAP or LIME into preach into result? Thank you.
Yeah, that's a good question. I'm not sure I'm qualified to say which one's the best. I guess my biggest point that I would say is I would caution against using them for coming up with sort of a hard story. Do you know what I mean? Like, so looking at this one, and I think this is just looking at average activation maps sort of early on. Actually, I'd have to think about how they got these. And so Lime is similar, right? So it's looking at activations that, trying to remind myself. So it's looking at activations that lit up and then went on to influence the classification decision. And it tries to relate that back to local information here in the beginning. And you know, you get these maps and they look somewhat reasonable, and you can come up with sort of a story for yourself about why that map makes sense for a given class. Certainly this is just a class saliency map. Certainly it looks good for a dog. But I think, you know, there's just so much expressivity there to come up with something that you already believe, I guess, that it's just ripe for confirmation bias. I don't know. Like I said, I mean, I think they're very pretty. I think they're theoretically interesting to look at. I know Lime is a pretty good one. Layer-wise relevance propagation is another one that I've used, and it's pretty good. But yeah, I don't know. I just, at least in medical imaging, for the case of discovery, I don't think they're useful. I wouldn't give you like, oh, if you use this one, it'll be fine. You know, I don't feel comfortable saying that.
All right. Hey, Nick, there is a question from Sarah, and the question is, in the training set, do all the images come from the same scanner hardware?
For KITS 19, we actually had one of the more diverse data sets. Wonder if I could pull up, I'm not sure I'll be able to get to it quickly. So we had, I think, something like 80% or 85 came from Siemens, because we're heavily Fairview. So the data came from mHealth Fairview at the university and at Fairview Lakes and at Fairview Ridges. So all these different Fairviews in the metro, and they're very heavily Siemens. So that's why we had so many Siemens. But we also had, since the U is a referral center for urology, we had a lot of sort of primary care clinics show up as well. So there was like, you know, a lot in rural North Dakota and northern Minnesota, and some from eastern or western Wisconsin. So we actually had 77 different institutions that were represented with at least one scan contributing to our data set. And so that's where a lot of the other brands come in. Like, I think 10% might have been GE, and then, you know, something like 6% was Toshiba, and there's some that I'm doing a disservice to by not remembering. There's a fourth one. But yeah, I mean, in general, that's a pretty diverse data set. Having, you know, 20%, that's not the mode. The most data sets, like the BROTS data set, or the LITS data set, is very standardized. The NIH pancreas data set, like most of those have just a single manufacturer represented. So to get a data set that's really diverse, you have to collaborate with other people, I guess. So Dr. Wade just moved to Cleveland. I think I'm going to be very interested to see what brand of manufacturer they have down in Cleveland, because if it's not Siemens, then that would be awesome for us. Then our results are going to be more general. I think you're muted.
Yep.
That's good.
Yeah. So we have another question here from VJ. Two questions actually from VJ. Are there any cases where data is annotated pixel by pixel? Have super resolution GANs been used to supersize masks made on low resolution images?
That's a really interesting idea. I don't know. You know, it's kind of a, it seems like a general rule that if someone says an idea and I'm like, I wonder if that's been tried, then like almost always someone's tried it, it seems like. But I'm not personally aware of anyone doing that, but it sounds very interesting. So I mentioned where is that? I cautioned against using the sort of helpers like that because I worry that here it is. And so I worry that helpers can introduce bias. So I would worry if we were using super resolution, like what sort of bias could that be possibly introducing on the shape of our masks or on how they align with the underlying anatomy? But it's entirely possible that it would just work and work really well. Because then you could do your annotations on a smaller scale, and that could potentially be faster, and you could still come up with really good masks. So that's a very interesting idea.
Yeah. All right. We also have a question from Kate. First, she makes a statement. She said, Nick, it sounds like you have great common sense to think about the impact that the work has on providers and patients. And you mentioned the input you had received from a pathologist. Do you have a process you use to get input from medical experts and the patients?
So I work very closely with Dr. Chris Waite, who is now at Cleveland. So it's going to be a little harder, but we still meet, weekly to discuss these things. And in the summers, we have these, we call them a Client for Kidney Cancer Scholar program, where we fund research for some medical students every summer. And we work with them to basically collect more data and then do some hypothesis testing that's sort of ancillary to these studies. And I love getting the medical perspective from them as well. But I do have to say that forming interdisciplinary collaborations like that is really hard. And I was extremely lucky to sort of fall into this project with a lot of these connections already made. So I did my undergraduate at the University of Minnesota, and as I was finishing and looking at PhD programs, we just happened to get this NIH grant to do this research on kidney cancer. And I had sort of started on that when I was a senior undergrad, and there was a senior PhD above me that had also been sort of leading that project, but just for a year at that time. So he had sort of done all the legwork to find a good clinician to work with, to find some medical students that were willing to collect some data, and start building those bridges and get the ball rolling. Because it really did take about a year before anything productive really happened and before we built a good enough relationship to do this research. But now that we have that, it's so valuable to be able to have that exchange and to meet regularly. And, they teach me about medicine. I try to teach them about machine learning. And, we also try to hold seminar series. We created a journal club called MAML, Medicine and Machine Learning for medical students. So that's just kicking off. Unfortunately, COVID really sidelined the in-person portion, but I really hope that kicks off in the fall or spring or whenever we can. And yeah, I think it's just all about getting people with different backgrounds in the same room and talking. The more you can do that, the better. Oh, and the patient perspective, that was one thing I didn't touch on. I think, patients are really the biggest stakeholder in this. And, unfortunately, we really haven't been able to get the patients in yet and understand their perspective. We did do one study where we went to the state fair and did surveys, and we asked people a few things. One of them was if an AI disagreed with your doctor on what you should do about your cancer or something, which one would you like to do? And it was pretty split. People either wanted to go with the doctor or they wanted to go with the AI. It was something like 60-40. I think the AI won. But people were really adamant about their decisions. Like there were some people that were super scared of anything the AI had to say. They said, I just want my doctor. And others were like, no, screw the doctor. I want what the AI says. They're unbiased. So it's going to be really interesting to see how cases like that play out in the real world. I think, clinicians are going to have to figure out how that counseling should work in cases where maybe there is such a disagreement.
All right. One question I have, So you mentioned about AI complementing a skilled practitioner. So like what orders of magnitude do you think AI coupled with a skilled practitioner could reduce the costs of a patient going through, kidney cancer?
Yeah, cost is an interesting one, right? Because it depends on how much you charge for the AI system. And yeah, I don't know. I think the biggest opportunities, the ones that, the deep learning researchers love to talk about is in radiology and pathology. Because radiologists, all they do is sort of signal processing, right? At least that's what, deep learners like to believe. They look at an image and they generate a report, and then they look at another image and generate a new report, right? So that's an image captioning problem to them. And they say, okay, we're just going to train a system to look at medical images and come up with a radiology report. So like people like Jeffrey Hinton, who in a speech in 2014 or 2015 said we should stop training radiologists now. He said it's just completely obvious that we're not going to need them in 5 or 10 years. So there's that extreme point of view. I'm more in the other camp. I think we still need the radiologists. If anything, they're super overworked right now. Pathologists too are signing out cases long after 5 p.m., a lot of the time, doing it faster than they would like to. What I would like to see is a lot of the standard, the easy boilerplate cases, those will be taken by the AI. And then, the harder cases that the pathologists and radiologists want to spend the more time on, we'll be able to allocate the time that they want to those. Their time will be freed up to do more productive things like that, rather than being crunched. So that's my general opinion. It could be that, there could be some work displacement in radiology and pathology, but I don't think it'll be anything significant. Not in our lifetimes, I don't think.
We have another question from Vijay. Do you have any tips for finding medical professionals that will be able to give insights or data?
There's no harm in cold calling people. I think, I just show up at their office or, shoot them emails. Clinicians are generally very busy people, but they're also, they understand that these things are going to be important in their field and they want to help with that research. Yeah, I mean, it's unfortunate because like the first thing that we as deep learners need when we go to clinicians is data, and that's like the least fun thing for them to get and annotate for us, right? So like the more that we can show that we're interested in what they're doing and want to have a deep understanding of it and are willing to like learn and participate in the data collection and annotation, I think you have to really phrase it as a two-way relationship rather than just like one way, you're going to provide me data, The other thing I would say is, it is a lot of legwork to establish that relationship. So if you can find a lab that already is doing this sort of interdisciplinary work, then that's great, but they are pretty rare, right? So you do what you can. Our lab is doing that at University of Minnesota under Nikos. I'm not sure I'm aware of even one more faculty in computer science, maybe one that's working closely with clinicians. But I would say most institutions have 1 or 2 labs that you could look for.
Let me unmute myself here. So we have another question from Kate. Kate is wondering if reaching out to us. Okay, a statement. So I think this is just adding to what you said. So to Vijay is I wonder if reaching out to associations either for specific health condition or for medical professionals would help to find people willing to give input. Did I read that correctly?
That sounds like it. Yeah, I mean, there's a lot of initiatives right now in like giving patients agency over their own data. And then in that case, patients might be willing to sort of pool the data on their own for research purposes for specific diseases, maybe. I think for rare diseases, that could be an awesome way to work because If I go to a clinician at the University of Minnesota and say, I want to work on a rare disease, they're going to say, well, I only have access to, you know, the population of Minnesota, and there might be 3 or 4 cases, you know. So how do we establish sort of networks of data sources from all over so that we can work on diseases like that? I think you might be muted.
Yep. All right. So with COVID-19 very prevalent in society today, what's the extent of image collection for, you know, lungs and just I want to say organs affected by COVID? Has there been like a very strong push to get a lot of images to train these models and stuff like that?
Yeah, I'm really not an expert on the chest. I know I'm far more comfortable looking in the abdomen. So I know of co-rads. So you may not know these rads things that people say. So there's something called pi-rads and li-rads and chi-rads, and these are all different, basically radiologic scoring systems for different types of cancer usually. So li-rads is for liver cancer, and you get a numeric score. Pi-rads is for, I think, prostate, and you get a specific score. Bi-rads is for breast. And they've created one for COVID called co-rads. And the goal is to basically risk stratify patients according to characteristics of the, I think, damage to the lungs. And I know I saw a paper like yesterday that was trying to reproduce co-rads using semantic segmentation of damaged tissue in the lungs and doing segmentation-based characterization to produce that score. Didn't get a chance to look in detail, but I'd love to look further. If I find that one, is there like a way I can send that to the group or post that somewhere? I don't know.
Yeah. Just share with me, and then I will post it. Okay. Yep. By the way, I want to comment that Nick was kind enough to allow us to record this conversation. I mean, the presentation. And because we got requests from a couple of folks who really wanted to attend, but they couldn't because of other commitments. So I'll be sending out, or Jen will be sending out a link to this recording in the next week or so. Okay. All right. Perfect. All right. We have a comment on, from Nick here. So Nick, no, Vijay, not Nick, sorry, Vijay. I'm working on a project that's using lung ultrasounds to diagnose COVID. So please reach out to me if you're interested. Yeah. So if actually if anybody in the meeting here is interested, please reach out to Vijay.
Very cool.
Yeah. Yeah. Any other questions? Let me scroll through the chat here to see if I missed any. Yeah. I don't think I did. All right. All right. Any other questions? All right. Oh, comment here from Sarah. This has been amazing. Thank you for the work you're doing, Nick. That's awesome. Yep.
Of course.
Yes. Yeah.
Like I said, I think the most interesting work is at the intersection. You know, it's great to be in computer science or AI because you can take those skills to anything and try to do some problem solvings, and you learn, you know, cool stuff about whatever application you're working on along the way. So I've had a lot of fun, you know, learning about medicine, the little bit that I've learned, I guess. I'd love to stay in this space.
Nice, nice. Yep. Yep. Cool. All right.
All right.
If we don't have any questions, I want to say thank you to Nick, and thank you to all of you for joining us this evening. It's a gorgeous evening outside, and you decided to spend almost 2 hours with us. So thank you. We appreciate that. Awesome. All right. Thank you, everyone.
Thank you.
All right. Bye-bye.